Yes. Okay, yeah, so hi everyone. Yeah, I'm sorry for being so late to this conference, but I'm glad I made it in time to tell you about supersonic turbulence in the CGM. And surprisingly, my talk will actually be an alternative model for carbon for Andy Fox's question, last question in the previous talk, and it's something instead of interfaces. But we'll get to that in the end. Yeah, okay, so one more thing. Most of the work I'm going to show you is based on the work of my graduate student, Aaron Kakuli. Okay, so to kind of set the stage, I want to raise a very basic question. What do we mean when we say that the CGM is multi-phase? Okay, and I would assume that when I ask most of you this question, the picture that comes into your mind is that there is kind of a hot volume filling medium. Okay, in the Milky Way mass scale, we have 1,000,000 degrees, the temperature of 1,000,000 degrees Kelvin. And within this volume filling medium, you have localized cool gas structures, okay, clouds or mists or filaments. And kind of the intermediate temperature gas comes from the interface between the cool clouds and the hot volume filling phase. Okay, so that's, I think, kind of what we would consider the standard paradigm for a multi-phase CGM. And what I want to do in this talk is suggest that this paradigm is not always correct. Okay, that in some cases, okay, specifically in the inner CGM at high redshift, we need to create a new paradigm for the multi-phase CGM. Now, the motivation for this comes from this analysis of the fire simulations, which shows that the hot gas, the hot background is largely absent, okay, at the Milky Way mass scale in the inner CGM above a redshift of between 0.5 or 1, depending on the exact simulation. Okay, so you can see this absence both in these temperature maps on the top, which shows kind of the gas in the inner CGM and central galaxy. So at redshift 0, you see kind of a volume filling hot phase surrounding the cool gas disk with kind of these small clouds embedded. So at redshift 0, it's pretty consistent with the standard paradigm. But if you look at redshift 1, you see a very different picture. Okay, so surrounding the galaxy, the gas is mainly cool. Okay, so the hot gas is limited to these kind of small, localized, and transient clusters, clouds. Okay, you can also see this if you plot the mass fraction of the different phases within a shell of 20% of the virial radius as a function of time. Okay, so again, you can see that at early times, the hot gas mass fraction is very small, 10 or 20% of the total mass. Only at late times, okay, the hot gas mass becomes dominant. Okay. Okay, so at least in the fire simulations, we see that a main component of the standard paradigm is missing, okay, at this mass scale, at early times. So what are the implications of this for our picture of a multi-phase CGM? So one implication is that it means that there's a change in the nature of turbulence in the CGM. So this is, you can see this by plotting, comparing kind of the turbulent velocity versus the mean sound speed. Okay, this is again measured in gas in a shell at 20% of the virial radius. And at early times, okay, when the hot gas is absent, the mean sound speed is very low, which means that the turbulence is supersonic. Okay, only at late times when the hot gas forms, okay, the sound speed becomes larger than turbulent velocity, and the turbulence becomes subsonic. Okay, so this formation of the hot phase is connected to a change in the properties of turbulence. Okay. Another implication of the change in the properties of turbulence is a change in the density distribution in the CGM. Okay, so what I'm showing you here is a distribution function of density, again, within a shell of 20% of the virial radius. Where on the left, I'm showing you a snapshot at redshift 0 after the hot phase formed. Okay, so here you can see kind of something consistent with the standard paradigm. Okay, you can see kind of a narrow peak with a tail to higher densities. Okay, and the narrow peak is simply the hot volume filling medium, and the kind of tail to high densities is just the cool clouds embedded in the hot gas. Okay. However, if we look at redshift 0.75, okay, so before, when the CGM was supersonically turbulent, before the hot phase formed, okay, we get something that looks completely different. Okay, it's simply a wide log normal density distribution. Okay, something very similar to the density distributions that we see in the ISM. Okay, so it's just in cool, at least in cold gas in the ISM. Okay, it's just wide log normal density distribution. The width is very large, it's almost 2 decades. Okay, there's kind of a strong, a weak correlation that as the gas becomes denser, it also has a lower temperature. Okay, but the picture is very different, okay, in this case versus in this case. Okay, we only see the standard paradigm only at low redshift after the hot phase form. Okay? Okay, so the conclusion is that at least in the fire simulations, Milky Way mass scale, low, small radii, small CGM radii, there is an evolution of the nature of the multi-phase CGM. Okay, so at low redshift, at redshift near 0, we have a dilute hot gas volume filling phase with cool dense clouds and maybe the interfaces between these medium. But at higher redshift, we simply have a wide log normal density distribution. Okay, nothing like the cloud and volume filling phase picture. Okay, so this is the picture we suggest. And the next question is, what are the implications for UV absorbers? Okay, and this is very related to the results that we saw in the previous talk. Okay, so to kind of understand what this means for UV absorber, Aaron drew mock sightlines through snapshots in the fire simulations. Okay, so this is an example of a redshift 0 snapshot where the hot phase already formed. And you can see here the mock sightline, this dashed line here. This is us, and this is the background source. And he plotted the density of different ions along the sightline. Okay, so this is the density of doubly ionized silicon along the sightline. And you can see that in this snapshot, we get that significant doubly ionized silicon is seen in kind of these very narrow peaks. Okay, so it's these very small clouds embedded in the hot gas. Between these narrow peaks, the gas is 1,000,000 degrees. Silicon is much more ionized. There's essentially negligible fractions of doubly ionized silicon. However, if we look at a redshift where the CGM is supersonically turbulent, okay, where there is no hot volume filling phase, the picture is entirely different. Okay, so here you can see that the doubly ionized silicon essentially fills a large fraction of the volume. Okay, a large fraction of the line of sight has significant amount of doubly ionized silicon. Okay, so in this case, we have UV absorbers tracing cool clouds embedded in the hot phase. But here we have a UV absorbers essentially tracing the volume filling phase of the CGM. Okay? And of course, when you have lots of cool gas, okay, the strong absorbers become saturated, and then you can analytically estimate what their equivalent width is expected to be. Okay, so for the velocity scales that we expect at this mass and redshift, we expect an equivalent width of order 1 angstrom. Okay, so this is another nice plot that Aaron made. Okay, so what he showed here are maps of the different ions. Okay, again, for when the CGM is supersonically turbulent. And I'm imploring you to see that this is not a case where we have cool clouds embedded in a hot gas, but rather the ions are simply tracing kind of this log normal density distribution that we expect in a supersonic CG, okay, when the turbulence is supersonic. Okay, this is another prediction, okay, where he plotted the equivalent width of different absorbers as a function of look-back time. And what you can see here is that at the early times, okay, when the turbulence is supersonic, okay, the equivalent width is simply above roughly 1 angstrom. Okay, only after the hot gas forms and the turbulence becomes subsonic, only then the equivalent start to drop. Okay, in the supersonic turbulent phase, equivalent width is 1 angstrom, both in silicon-3 and in carbon-4. Okay. You can also do this for many more ions, and you can see that essentially for all main UV absorbers, okay, the equivalent width we expect is of order 1 angstrom when the CGM is supersonically turbulent. Okay, so it's a very robust prediction of this scenario. Okay, so we just started comparing to the data. So we started with very early data by Proctor et al. 2006, where they measured the number density of magnesium-2 absorbers with high equivalent width. And kind of the conclusion is that, at least to an order of magnitude, okay, the statistics of the high equivalent width absorbers is consistent with the supersonic turbulent scenario. Okay, so that's basically it. Okay, so 2 main points. One is that the standard paradigm that we have for the CGM is inapplicable, okay, for redshifts above 0.5 or 1 in Milky Way mass scale. Instead, we have something different, where the CGM turbulence is supersonic. It has a wide log normal density distribution, and it's predicted to have 1 angstrom equivalent width for essentially all strong UV absorbers.
Okay, questions? Yep.
Thank you, Jonathan. Very nice talk. I love that you have very clean predictions. I'm curious, how would you reconcile with lower redshift, as you say, less than 1 observations, where we see incidence of stronger magnesium 2 or carbon 4 is very high and very low in background?
Yes, so the transition redshift is very strongly depends on the mass scale. Sorry. So if you go to lower masses, okay, the transition tends to happen at lower redshift. Okay, so potentially, so it depends on what the mass scale you're looking at. Okay, so on mass scale, lower mass scales, you would see lower, you see the transition at lower redshifts. And of course, also if you have cool clouds, could have also a high equivalent width. Okay, it doesn't preclude, it doesn't preclude this picture. Okay, does that make sense? Okay.
More questions? Eric?
So I was interested by this wide log normal.
Yep.
But you're also showing gas that's over 2 orders of magnitude in temperature. So I'm wondering, what does the distribution of Mach numbers look like this? Do you see a transition? Are you expecting this is wide because you're actually tracing significantly different turbulent parameters?
Yes. Okay. So first, when I talk about Mach numbers, I only talk about the mean Mach number. Okay. So it's just I take the mean sound speed of the gas, and then I measure the velocity, turbulent velocity independently, then compare them. So of course, if you have a cool cloud embedded in a hot gas, okay, it will usually move supersonically turbulent relative to its own sound speed, but it will be subsonic relative to the hot gas sound speed. So this is a general, I think, case. Okay, yeah. But the main thing that's changing here is not the turbulent velocity. You can see it's pretty flat, things in simulation. It's mainly the sound speed, the average sound speed, which is strongly changing.
More questions?
The turbulent velocity, as you just pointed out, is pretty flat over time. So is the driving source always the same? What's the trigger of the turbulence that's so stable?
Yeah, good question. Okay, so that's kind of the next project. We're going to look at what is the source exactly of this turbulent velocity. There's 2 possibilities. There's accretion and there's the feedback. Okay, so we have kind of preliminary results that it's accretion and feedback both give you roughly the same amount of turbulent velocity. So I'm not sure we'll be able to separate exactly that. Yeah, it's a good question.
Why is it that how do you get the cold gas in the first place, and like later times does it become hot gas because it gets well mixed? Is it because of turbulence, or like why does that happen?
Yeah, so the basic this result that the hot gas just forms, it's mainly a cooling time versus dynamical time argument. If you do an average cooling time for the hot gas, and it's very short here relative to the dynamical time, and it's long here. Okay, so the thing is that once the cooling time of the hot gas is very short, it disappears. Okay, in the simulation. That's it.
Okay, while the next speaker sits up, we can take one more good question. If there's any.
How does this all depend on the feedback? I mean, is the feedback what is creating a lot of this hot gas in the first place?
So the hot gas would form also without any feedback. It just forms from the accretion shock. Okay, so the gas shocks, it will form a hot gas. Just then, if the cooling time is then short enough, it will cool back. The feedback does seem to make a difference. So Vadim looked at some aspects of this picture in TNG50, and the formation of the hot gas is not as sharp as you see in fire. So see a very strong transition in fire between hot gas absent, hot gas forms. In TNG50, it's much more gradual. Okay, and this difference is most likely due to how the feedback is implemented.
Okay, let's thank Jonathan again.